Yeah. Yeah. Okay. All righty. So yeah, I'll be giving a quick talk on integrated modeling of wavefront sensing and control for space telescopes utilizing active and adaptive optics. How the heck do we do things for STP? Um, yeah, and I guess I should say it's an asterisk for this is how we do all this for STP, along with a quick overview of why we have to do what we do. Good. PowerPoint moment. Okay, that's awesome. All right, I'll give a quick overview of the background because I assume people know why we do things maybe. So yeah, we have found exoplanets. They're pretty neat. We've discovered them all pretty much using indirect methods up until now. Transits, radial velocity. However, these aren't the greatest. They're not particularly well suited for detailed characterization. Should I stand up? I don't know. They're not particularly well suited for detailed characterization of these exoplanets. Instead, what we'd like to do would be direct imaging. It allows us to properly characterize these exoplanets at a much higher signal to noise ratio. But the problem here is that they are orders of magnitude fainter and separated by only fractions of an arc second from their host star. However, we have coronagraphs. These are instruments that allow us to block the starlight and see the exoplanets that are orbiting the star. For these instruments, stability is kind of the key to everything. For one, it allows us to take these long exposures on these faint objects, which exoplanets are, without any changes in image quality. But the problem with that is that if you have a space telescope, we're not talking about the ground because the atmosphere sucks. Even in space, we still have to contend with a variety of degradation scenarios. Surface errors on your optics, jitter of the observatory itself, beam walk as your observatory jitters or has pointing errors, thermal gradients that are changing every time you reorient the telescope, etc. It all sucks. And the problem with that is that these coronagraphs are incredibly sensitive instruments. Your key metric that you're always looking at is contrast. Linked to here from Aaron's old SPIE proceedings on when this project was CDeep, that you need nanometer level wavefront control to maintain 10 to the minus 8 or better contrast. If you want to go for 10 to the minus 10, like Future Habworld's observatory does, then you need picometer level wavefront control. But thank God we're not trying to do that, right, guys? So yeah, we need good wavefront control, and how we do this is driving active adaptive optics and closed loop control using wavefront sensors that keep track of what the light in our system is actually doing. Thankfully, we have a little bit of heritage that we can go on at this point. Active and active optics have already been demonstrated in space. JWST has an active primary and secondary. Very cool. Closed loop DM control was demoed by our father, Ewan, on the DEMI project over at MIT with some smart people. And some other people down the road at UMass Lowell, led by Chris Mandillo, dug a dark hole. Not quite in space, upper atmosphere, but yeah, close enough. But yeah, they do it on a big old balloon. And within coronagraphs, and specifically to point out DEMI, within coronagraphs, you need a deformable mirror to do what we call dark hole digging, which is where we end up rejecting starlight from a region of the science image using some closed loop control algorithm. It doesn't really matter. And specifically, DEMI was the first project that actually demoed a working deformable mirror in space. Now, why do we need integrated modeling? So as I listed out earlier, we have all these different degradation scenarios that affect optical performance. However, how they affect our system is best modeled in different regimes for approximating the behavior of light. In our case, we need both geometric ray tracing and physical optics propagation. This is because for what is it? For something like thermal error, right? You have optics shifting. That is something that you cannot actually model in a physical optics model. You have to trace the rays to then tell you geometrically how does that change the performance of the system versus, oh, you have some high spatial frequency error on an optic. Well, to model that, you need to actually do the diffraction calculations that affect that instead. So we need to integrate all these things together from separate structural and thermal analyses, or approximated. I don't know. I don't remember the tangent that I went on at SPIE with you and Zernike's here. We'll get into that later. This slide doesn't explain it very well. Well, I think the main thing that I want to say here is one way to sort of parameterize or approximate errors when you don't have a good model to go off of that Ewan and Jared prefer is using a power spectra. In this case, you can see power spectra for a whole bunch of different Zernike's. And you'll see later how this pops up specifically for our model of the telescope and the WCC instrument. But these are temporal PSDs that tell you how these Zernike's are going to change in time. And again, you'll see that better later. But yeah, this lets us, one, parameterize the errors so that when we do have a model that can then tell us how the system is expected to behave, if we've already run our analyses on sort of quote unquote synthetic errors that we generate from these PSDs. Oh, if our updated model in the future gives us parameters that falls within the parameters defined by our PSD for like, oh, the system works, we can at least have a first guess at saying, oh, yeah, no, it should probably work. But anyways, let's actually get into the models. So for the telescope and context camera, we have a compact 3-mirror anastigmatic design described in Daewoo's 2023 SPIE proceedings. We're nominally operating on a wavelength of 650. The bandwidth, that's a lie, it's not 15%. Apparently it's like 23% or something nowadays. I don't know. The mirror is 6.5 meters. The secondary is about 20% obscuration rate. You can read. And I don't know, this all doesn't matter too much. Okay, yeah, and then so things to note. We have a couple ways to control what the light is doing in our telescope. One, our M1 has bending modes. It has a bunch of actuators in the back that can push and prod at the whole thing. And we have bending control up to roughly Zernike order of 37. And in addition to that, we also have our secondary mirror mounted on a hexapod, and that is mostly just to control low order, specifically focus and coma. Everything else we would then offload to the primary mirror, which can ideally bend out the rest. Now, how do we actually model this? And the telescope is the more interesting case here. So starting from the top, anytime we want to simulate a PSF on our telescope, we start with a ray trace. The physical optics model and the ray trace are linked together. That's the whole integrated modeling part of this all. Before you actually do a diffraction calculation, you first go to your ray trace model and tell it, hey, at this field point, trace me some rays and tell me at the exit pupil, what is the wavefront error caused by geometry? And you get, some small low order error because we have a nice design. Thank you, Daewoo. But that is not everything that's present in your system. Like I said earlier, your optics aren't perfect. You've got, surface roughness riding on top of all of those optics, and that's going to diffract your light in funny ways and degrade your performance as well. So what we do is we take that low order error that we've calculated from the geometrical ray trace. So that coming from the ray trace, on top, we add on top of that our high order errors coming from the optic surfaces. And then on top of that, this is other low order error. This is what I'm talking about earlier with like sort of the parameterized disturbances. In our case, we have those PSDs for the Zernike's describing how they change in time. That is supposed to model how the thermal environment will change the incoming wavefront of or will affect the wavefront of our telescope. So we have some custom Python code that, takes those PSDs in and spits out some like low order wavefront following those PSDs. We add those all together to get some cumulative wavefront. And with this, now we can do a proper diffraction calculation with our physical optics model and get a bunch of PSFs. Yeah. And then we always propagate a focused PSF. And we also propagate a couple of defocused PSFs as well. And that is because we want to do phase retrieval. So yeah, I can say this here because you guys work on the project. What is it? So on our our telescope focal plane, we do not just have a single detector; we have a detector array. And our method of getting defocus diversity to perform phase retrieval is by having basically slightly pistoned detectors that are just a little bit out of focus. And so, yeah, that gives us, slightly out of focus PSFs. With this defocus diversity, we can run a phase retrieval algorithm. In our case, we choose to use algorithmic differentiation along with a nonlinear optimizer to get an estimate of our wavefront error. And then with that estimated wavefront error, we send the defocus and coma modes of that to M2. M2 corrects for defocus and coma. And then the leftovers we send to M1, and M1 bends out those higher orders. So yeah, so this shows a lot better what those earlier, that big graph of meaningless PSDs was there, what that meaningless, all those PSDs meant earlier. So each one of those Zernikeys, or each one of those PSDs, right, I said describes the temporal evolution of a specific Zernike mode. Zernike modes, evolving temporally. These come from those PSDs. Add them all together, you get this. And as you can see, because it's, well, I mean, the resolution's terrible, but you can see a little bit of fuzziness. That's the higher order errors all sort of riding on top of it. You can see it at the very beginning before all these start really evolving. But you can see, given that those PSD parameters, if we don't control anything, thermal kind of ruins everything. This is bad. That's 700 nanometers of RMS wavefront error. That's going to ruin everything for us over the course of 30 hours. But we do phase retrieval. We use that phase retrieval to send corrections to M1 and M2. And holy moly, it's stable. Yeah. Just look at it for a bit. Look at how stable it is. Isn't that neat? So yeah, so at least in simulation, things work. We can maintain roughly 30 nanometers RMS wavefront error. And at least for this simulation, I had some jitter or photon noise detector noise all injected in there. And we're assuming 60-second exposures on a, albeit relatively bright magnitude 17 star, but yeah. And then, yeah, what's it? There's a bunch of leftover spherical. I don't remember my explanation for why that was the case. I think it has to do with the bending mode specifically struggling to bend out spherical because, right, spherical is just, you go out to the edge of your aperture and then, oh no, your wavefront goes crazy. It's hard to bend a mirror like that without just kind of breaking it. So I think residual spherical was one of the issues from there because of that. And then, yeah, we also characterized how well our phase retrieval algorithm can estimate wavefront errors. Depending on basically star magnitude. Ewan made me convert it to focal plane SNR, but really what we care about is star magnitude. Yeah. But basically what this graph shows is that roughly for an RMAG of 20 on our guide star, we can do phase retrieval just fine. That corresponds to a PSF SNR of roughly 500. And based off of the conversation I had with Doug the other day, I figure I should also specify that when I say SNR here, it's more signal to background. Is that what?
Signal to background noise.
Yeah, signal to background noise, where essentially I was literally just dividing the peak of the PSF by just a patch of noise in the corner of the image. So really when I say an SNR of like 500, we're talking around between 500 and 1,000 counts there, actually on our detector. But yeah, it works down to magnitude of 20-ish. Now, so that was the front end. That was the actual fun sort of integrated modeling part. The other part that I simulated was our BBC. I pretended for the presentation that I'm just simulating Scoob, but really it's the ESC. Again, wavelength at 650, bandwidth 2%, probably going to have to be higher now, but we don't talk about that. Uses a smaller entrance pupil. I'll get to that in a second. Blah, blah, blah. You can read it. So this model is all physical optics because we don't care about geometry because everything's on axis. How convenient. So for one, these corrected 6.5 meter full aperture wavefronts, we feed our coronagraph into 2.4 meter sub aperture. So we just take one of these sections in between the struts there, and then that's what we actually send into the coronagraph. Why do we do that? We're using a vector vortex coronagraph, and vector vortex coronagraphs do not play well with any sort of obscurations in your pupil, because obscurations in your pupil, you have big wings on your PSF. Those big wings don't get nulled by the center of your vortex, so it doesn't work. So that's why we do that. So in reality, we have a 2.4 meter aperture coronagraph. That wavefront gets sent to a DM. We're using a 34 by 34 kilodm from Boston Micro Machines that we have in the model. And then that DM corrects the wavefront even further before we send it to our charge 6 vector vortex coronagraph. If this is phase, you can just see it ramps around 12 times because charge versus how many times you actually go around, it doesn't really matter. And then, so this focal plane mass diffracts your on-axis starlight, the edges of your pupil. And that's super convenient because then you can have a slightly undersized aperture stop in a pupil plane after that to reject that starlight and leave you with ideally like no residuals in your focal plane. However, we have problems, right? So there's going to be residuals in the form of speckles. Also worth noting here that we don't just have this undersized stop. We are using a wavefront sensor known as a self-coherent camera, which I'll get into earlier. And to make that work, we introduce this extra little pinhole off in the corner, and that allows a small amount of starlight to leak through as well to the focal plane. So yeah, you end up getting this final science image. Because our wavefront isn't perfect and we don't get perfect nulling from our focal plane mass, we end up with all of these speckles. And these speckles are on the order of like 10 to the minus 4 or 5. I don't really know. So we need a way to, dig down several orders of magnitude if we actually want to try to find a planet. So first step of that, we need a wavefront sensor. And like I said, we use a self-coherent camera. And this is just a very quick diagram kind of showing you how we actually do a wavefront sense with this. So you get your science camera, or you get an image off of your science camera. Because you have this off-axis pinhole allowing a little bit of light through, it comes in at an angle. What's it going to do with your speckles? It's going to make fringes. That's super cool because then when you take the Fourier transform of your image, you get your central OTF as you normally would, but you also get these two sidebands. And these sidebands contain all the information from the speckles. So what you can do is you can shift it to the center, crop everything else away, inverse Fourier transform, speckles. Holy moly, we've estimated our speckles. Yeah, that's basically it there. There are other methods of focal plane wavefront sensing as well. Pairwise probing. Yeah, that's actually it, right? I think it's literally just pairwise probing. Maybe LDFC does something, I don't actually know. But the nice thing about an SEC is that you can do focal plane wavefront sensing in one image. Your fringes are always there. You take an image, you see the fringes, you can do this. Versus with pairwise probing, you have to send your DM a set of probes. And for each one of those probes, you're taking an image. And then you're using that set of probed images to then estimate your wavefront. So you don't get full uptime or like 100% duty cycle, if you want to think of it that way, on your wavefront sensing. Oh, and also worth noting that a self-coherent camera enables differential or coherent differential imaging as a post-processing method, again, with a single exposure. And that is because, and this is sort of where the coherent and the self-coherent camera part comes in, that off-axis starlight that comes in, it is going to interfere with your speckles. However, it is not going to interfere with any planets or disks that are there. That's because the starlight is going to be coherent with itself, but it's not going to be coherent with a planet or the disk. So if you're able to estimate the coherent portion of the image, aka your residual speckles, your OTF also contains the rest of everything else that's in your image. That includes the incoherent portion. So you can get the incoherent portion, subtract away the coherent portion, and that leaves you with, well, the incoherent portion, which should be, planets and disks and such. So it's also just post-processing for free. So it's cool. But yeah, we can use that model, dig some dark holes. So again, as I was mentioning earlier, all we're doing here is sense the wavefront, and then you figure out what deformable mirror command will, what deformable mirror command will make it so that you have this region of destructive interference where you're interfering away the speckles, leaving ideally a planet or a disk there that you're trying to find. There's none in this simulation. In this case, with this model, we can reach sub 10⁻⁸ contrast with some jitter, detect noise, photon noise, and we're assuming 60-second exposures on a magnitude 3 star with 30 nanometers RMS wavefront error. Wow, that's not that much. Yeah, there's more now, but yeah. We'd still get 10⁻⁸, so it doesn't really matter. And then also did sort of a similar, looking at the photon noise limit for dark hole digging, depending on star magnitude. And again, SNR is a stupid metric for this, but really we can dig to below 10⁻⁸ contrast for a star with an R mag of roughly 6 using our 2.4 meter aperture. So, yeah. And then dark hole speckle SNR, similar ideas before. I'm just looking at a speckle and then comparing it to just flat background noise. So, yeah. So, in conclusion, we've created some integrated models for our big old 6.5 meter space-based observatory. It can simulate both a context camera and a vector vortex coronagraph. We've been using them to demonstrate closed-loop control of the telescope and for dark hole digging and maintenance. And then for this specifically, we also established the photon noise limit of both instruments. In the future, we'll keep continuing improving our models, establish boundary cases for degradation effects, and that's what I still work on. But yeah, that's basically it. Ooh. Hopefully that was helpful. Yeah. So anyways, feel free to ask questions. I figure probably the most important things to look at are the models for use on shit. So yeah, if you have any questions there, let me know. Now or later, doesn't matter. But yeah. Where is it? Yeah, this one's probably the most important thing. This is honestly the only really complicated thing about models, is just the fact that when we're simulating the context camera, we have to perform a ray trace in the background the whole time. So that's basically it.
So if you're running a ray trace in the background and the ray trace is, what is it calibrating? It's not surface errors. What are those errors coming from?
Geometry, basically. Was it a 3-mirror anastigmat, as far as I know, is like analytically solved so that like you can get a design where on axis, perfect wavefront, that should be nothing, right? However, we have this quote unquote compact TMA design where we're just trying to shove everything, axially as close together as possible. And to do that, what is it? We have to miss this little M4. And to get around that, what Daewoo did is he introduced a small field bias. into the observatory. So if I were to actually draw like the rays coming into it, they wouldn't be coming in perpendicular. You know what I mean, right? They wouldn't be coming in straight on like that. There's a slight tilt to that. And because a TMA is not perfect, or isn't going to give you perfect, what do you call it, performance when you're slightly off axis like that, you're going to have a small amount of essentially field dependent aberration.
So basically, my question is, if your telescope sort of alignment and everything's fixed and it's in place,
Mhm.
and that depends on basically your alignment and where you are in the field of view, is that not something you can solve once and store in the background? Why are we running in real time?
Okay, I see what you mean. Uh, yes. So if you're assuming your telescope is static, yes, you could just do that and store all that. But in our case, we want to simulate one. The biggest problem with that is thermal. Those changing thermal gradients are going to slowly shift your optics around, and when that happens, that's going to induce misalignments.
But you have a separate thermal component.
Yeah. So this is why I hate this. Um, yes. However, in the future, we're going to have a structural and thermal model that actually tells us how the optics will move. And then that's what will feed to the ray trace. The ray trace will evaluate, okay, how do those misalignments screw with my wavefront error? And then that is actually what completes the loop. It just happens to be that in this case, we still don't have a structural thermal model. So all of our structural and thermal errors are made up. They come from those PSDs.
Okay.
But we still do need the ray trace because we're using M2 to perform corrections. We still move M2 around. So simply because of that, we still need to perform the ray traces because every time we move M2, it's a misalignment. Granted, it's a misalignment we want because it's correcting for something else. But what's it? We still need to figure what that is from the ray trace. We can't do that in visible optics land. Fraction there. Yeah. I think those are the two main things.
And then were photon noise limited with like an SNR of 500 R magnitude of 20? So
Yes. But this was something I was getting into with Doug the other day. My understanding of SNR is probably just wrong. Like this is PSF peak to detector noise ratio, essentially. Detector slash photon, or just a patch of like nothing in the corner of the image. Take the average of that noise, and then take the peak intensity of the PSF, divide into two. That's the SNR here.
Yeah, I was also confused by a dark hole SNR because you said something about
speckle SNR.
Speckle SNR is with respect to your background.
Yeah, so it's a similar thing where just still take a corner of your image where there's like no light there, so it's just purely noise. Take the peak intensity or the peak counts from a speckle and then divide the two. So that's the SNR there. It's not proper SNR because there's a bunch more terms that go into SNR. So yeah, something that's not super clear that is. I don't think anything else important that I'm missing.
Yeah. So when you're doing the coronography and you've got your third magnitude, sixth magnitude star, whichever it is, and you're getting down to 30 nanometers there before you dig your dark hole, is that reduction down to 30 nanometers all from doing like your self-coherent camera stuff? Is that?
Oh, sorry.
Or does the context camera have to do anything to support this?
Yeah, it does. I don't know how much it has to do. Yeah, I don't have a good answer for how much the context camera has to do, but I think it's a similar case to, what do you call it? The spectrograph, where it's, well, not quite. We care about performance. The context better, or the telescope better be correcting it to some degree. But at the end of the day, it's more about stability and just keeping the input, like, yeah, just stable over time. What's it? I was also, this 30 nanometers of injected wavefront error, that is static. That is the static wavefront error coming from the optic surfaces. And then on top of that, I add, what is it? This corrected wavefront error coming from the telescope. And then I assume it's static. And I make that assumption because, what is it? In the correction loop, it stays pretty static. But then, yeah, all that stays static while I actually dig the dark hole. So we're not really changing like the wavefront error or OPD. What's it? The DM just adds some shape that does destructive interference over there.
Okay.
That answer the question?
It did.
Okay.
Thank you.
Just want to make sure. Yeah. Does anybody else know? Did I leave out anything important?
Do you have a reference for the current sort of phase retrieval algorithm that we're using? Is it the FineUp?
Is it the final? No.
No, is it the FineUp?
Oh,
Which specific algorithm we're using?
it's all just drilling FineUp.
Oh,
The drilling and FineUp paper, yeah. Because this was all done using Kyle's old FDPR code, and that was also just the same drilling FineUp stuff, right? So it's all drilling FineUp, just all implemented slightly differently. So that's it there. And then yeah, in terms of like things that have changed about the model, like not too much. It's really just been me throwing a hissy fit and trying to use Prism more instead of Poppy, but pretty much everything the same. There's talks about wanting to increase the throughput, I think. I don't know, because we have, or sorry, increasing the bandwidth because the throughput of our chronograph is so terrible that one of the easier ways to just get more photons is increasing the bandwidth. But I don't know. Apparently, Ewan's on some side quest to see if we can coat the mirrors with silver or something. I don't recall.
so the 15% bandwidth that you mentioned, like the early slide, that's the bandwidth for the whole array of detectors that are being used for phase retrieval?
Yes. I think, right?
We're using
Sloan R band.
Sloan R band.
Okay.
filters
Okay.
for phase retrieval.
Oh yeah, so that's what I was saying. It's changed now. In the simulation, I assumed 15%, but now it's actually the defocus detectors for phase retrieval use Sloan R band filters.
There's just a single filter in front of the whole array.
No, each one has its own.
Oh, okay. But the one we're using for phase retrieval is the Sloan R.
We have 21 sensors, 18 of them are going to be defocused by different amounts that Kevin's going to tell me how much I should defocus each one of them.
Okay.
Yeah.
And we're making them all the same filter so that he doesn't have to do a color correction on top of everything else.
Yeah.
Okay.
Unless we want to add spectral diversity. Does that, wait, Kyle, did you ever run simulations on that? Does that give us anything?
I never found a benefit of doing it.
Okay.
I tried it.
Okay, cool. I'm happy with that because it means that because that's just more complicated for me.
I mean,
for the algorithm.
in principle, you'd think you'd be able to, right? Like,
Yeah.
because like with interferometry, right? If you choose two, like if you had two really narrow band passes that you put next to each other, right? In theory, you could use that information, generate like a synthetic wavelength that's very long. It could give you lots of dynamic range.
Mm.
One, I think photon noise kills you, right? Because you have to use narrow filters. But two, I never actually found that that actually helped. And then even if you assume like larger band passes and then just pick a few, I never found that that really did much. It's worth re-exploring because like, but I've never seen anyone in the literature actually doing it. I've seen people like listed as a type of diversity for phase retrieval, but then I've never seen an explanation as to what it actually gets you.
I see. Okay.
So,
Maybe old Jimbo's holding on to something there. Who knows?
This is probably like in the broadband implementation of the phase retrieval algorithms, like those papers, where they applied like broadband filter.
So, I mean, there's different ways you could implement it. I mean, in broadband, you don't really have wavelength diversity because you just get an image that's basically integrated over that full bandpass. Rather than having like multiple images in different bandpasses. So, but the answer seems to be going broadband gives you more photons, but it almost always hurts your performance in terms of phase retrieval.
Yeah, this is something I've never looked into before, but our performance is down like 30 to 40 nanometers, but our bandwidth is 15%, 650, that's like 90-ish nanometers. Are those two not related somehow? But I mean, if our sort of photon flux has a spread of 90 nanometers, but we can correct the wavefront down to 30 to 40 nanometers?
I don't know if you expect a relation between those.
Yeah, I was just curious. I don't know if there is.
Like definitely going broadband adds some uncertainty. I think you don't know, at what wavelength you're seeing this contribution, they get this speckle and things like that. I don't know that you'd expect there to be some kind of like uncertainty relationship between those two. I don't know.
I mean, presumably that's why the correction would degrade with the broader filter, right? Like you're just adding too much of a range and wavelengths. So you're not able to sort of correct with interferometry. And I haven't looked into this. I don't know about this. It's just like, I don't know how does this work?
Yeah, I don't know. Yeah, like I don't think. I mean, like maybe there's something there, but yeah, I'm inclined to agree with Kyle. Or it's just I don't know how more or less wavefront error would affect. Well, I mean, obviously less wavefront error is better, but like, yeah.
Yeah, I don't know. It is weird though, because like if you assume you don't have any chromatic elements in your system, then you know exactly how like the phase evolves with wavelength given an OPD, right? So it seems like in principle you could, by running this in the reverse mode, find that solution exactly.
Yeah. I guess maybe could you make an argument that like what's it?
Is it related to like sampling or something?
I think once you hit like
We're well sampled.
yeah, we're well sampled. So oh yeah, what's it? Because it is worth noting too that when I report this estimate error, this residual RMS that you're seeing is really just the high order stuff that yeah, it's not a super fair metric because I'm only telling phase retrieval to estimate up to Zernike 37 because that's what we can control. But obviously there's all this, high order stuff riding on top of that. And so that's really what this residual is. In terms of estimating the low orders, it does that quite well to within like single nanometer precision. So yeah. But with the broadband thing, is there an argument to be made where it's just like your OPD is going to induce the same speckle pattern, but it just gets scaled with wavelength?
Yes.
So it gets scaled, but then I mean it's also it gets scaled, of course, right? But then it's also like if you think of it in the in your complex exponential, right? It's a smaller portion of your wavelength. So
I see.
Fractional wavelength also decreases with going
Yeah.
the point is, it's very analytic. We know exactly how
Yeah.
it scales.
Yeah.
So I think in principle, you should be able to exactly recover it. And I don't remember when we do broadband without any noise, if we're able to get to like effectively, single nanometer RMS residuals. It's been long enough since I worked on this that I don't remember.
Yeah. I mean, with whoops. Here, let me just reshare this. Yeah, I mean, we're more or less able to get without noise because all of the simulations I'm doing nowadays don't have noise. And yeah, you can get down to like single nanometer.
And that's even going broadband.
Yeah. Like what's it? That thing that I posted yesterday, even with like added defocus error, like give it a few iterations to go back and forth. It got down to I think 2 nanometers.
But is it a polychromatic PSF or monochromatic?
Poly.
Yeah,
that was like a 25% bandwidth almost. So very large bandwidth, but still able to perform quite well. I actually haven't seen what is the bandwidth of the Sloan filters.
I just looked. It's like 22% for the R band one.
Oh, okay. So I think that's pretty close to what I'm actually doing right now. Then okay. Cool. So yeah, like we're able to get down there, and then yeah, obviously once I start adding noise, it's going to get more complicated.
the reason why I brought this up is I've only done this like on CAG, which is on ground, and they use like really narrow band, like iron filters, some iron line, and I think that's more related to the atmosphere. But here I imagine we're in space.
Right, so
you would just know.
It's definitely easier.
Yeah.
In a narrow bandpass, right? Like the closer you can get to monochromatic, the easier it gets. The issue here is we don't have the luxury of going and pointing at a bright star and then just getting tons of photons, right? We just need to pick random stars that happen to fall, and so we expect them to be very dim. And so then, yeah, there's a trade. And what we found with simulations is, it helps to go broader, even though it makes things a little more difficult. Because ultimately you end up hitting this SNR limit. However you define SNR.
Yeah.
Right, but there's some limit.
Don't take my definition. It's I know it's wrong.
Yeah. Okay. And then I had like a couple of minor questions, but I don't want to like hold people up.
Yeah, sure. No worries. I mean, I can
call it. Yeah.
I can stop by your office right after this. Yeah, we can just talk about it.